Okay, let's just dive right into this explainer. Today, we're tackling one of the most requested and honestly notoriously challenging enterprise setups out there. We are talking about building a rock-solid, production-ready SQL Server 2022 always-on cluster on Red Hat Enterprise Linux 8 using Pacemaker and Corosync. Now, if you're coming over from a Windows Server Failover Clustering background, well, buckle up. You're going to find that the Linux environment plays by its own unique set of rules. We're talking systemd quirks, very specific agent constraints, the whole shebang.
So think about the architectural end state we're actually building toward here. We've got our primary node, node 1, doing all the heavy lifting. Right alongside it, we have our two secondary worker nodes just waiting in the wings. And then the absolutely critical piece of the puzzle, our floating virtual IP address at 10.19.143.80. This virtual IP is exactly what your applications are going to point to. It completely abstracts all that underlying node health away from your app traffic. Pretty neat, right?
Okay, so to get to that highly available state, here's our roadmap. We're going to cover strict name resolution, then pacemaker secrets and endpoints, building the actual availability group, setting up those pacemaker constraints, and finally, a live failover demo.
All right, Section 1, the Golden Rule, DNS and strict name resolution.
Let's start with the absolute very first prerequisite. And look, as every sysadmin knows, it's always DNS, isn't it? Strict name resolution on Linux is completely, absolutely mandatory for SQL Server high availability. You literally cannot cut corners here. The node name that your SQL instance reports when you run select @ server name, it must match your operating system hostname perfectly. But wait, it doesn't stop there. Those names have to be flawlessly mapped inside the /etc hosts file across every single node in your cluster. Oh, and you also need to make sure port 5022 for the HADR endpoint and port 2224 for the PCS daemon are actually open in your firewall. Otherwise, these nodes can't even talk to each other.
So what happens if you just ignore this? Well, if there's even a tiny mismatch anywhere in your DNS setup or that host file, your availability group is going to fail instantly. No way around it. You'll just be greeted with endless download configuration timeouts or that dreaded error 47106. Honestly, getting this right on day one, it's a real game changer. It's going to save you hours of digging through error logs later on. Moving right along to Section 2, authentication, focusing on pacemaker secrets and endpoints.
So, moving down our deployment pipeline, we have to figure out how Pacemaker actually monitors SQL Server. See, Pacemaker isn't natively a SQL tool, so it uses this highly specialized resource agent called OCF/MSQL/AG. We have to follow specific steps to create a dedicated login file that holds our Pacemaker login credentials. And please, notice that exact 400 permission we need to set, along with the MSQL/MSQL ownership. I can't stress this enough. This is a massive stumbling block in Linux deployments. If systemd or SQL Server can't read this file because you've got the wrong ownership or, overly broad permissions, your MSQL Server service will just repeatedly crash on startup. Precision here is absolutely everything.
Okay, so once the Linux operating system actually has that secret file, we've got to tell SQL Server about it. We run a matching T-SQL script on all our instances to grant our brand new Pacemaker login these exact server state permissions. It absolutely needs to be able to alter availability groups, view the server state, and connect on the HADR endpoint. Basically, this bridges the gap. It gives the Pacemaker agent full, complete visibility into the health of your database. All right, on to Section 3, building the availability group. Now that authentication is firmly handled on both the OS and the database layers, we finally move to the primary node to build our external availability group. And honestly, this brilliantly illustrates the core difference in a Linux deployment. When you run your create availability group script, you have to include the setting cluster type equals external. Basically, you're explicitly telling SQL Server, hey, listen, don't look for Windows Server Failover Clustering here. Cluster management and orchestration, yeah, that's being handled completely externally by Linux Pacemaker. Once that group is created on the primary node, we've got to sync up our worker nodes. To do this, we perform a full database and log backup on the primary. Then, and this is super important, we copy those backups over and restore them on the worker nodes using the with no recovery option. That specific option leaves the database in a state where it's ready to accept transaction logs. Only after that's done do we actually run the alter database command to join them all to the availability group.
Which brings us to Section 4, the orchestrator, pacemaker resources, and constraints.
Next up, we jump into the orchestration layer. Guys, this is where the magic really happens. On our primary node, using our PCS commands, we define two totally vital resources, the promotable availability group clone set and, of course, our floating virtual IP. But look, just creating them isn't enough. We have to strictly govern how they interact. These two rules, absolute lifesavers. You have to add these exact constraints to Pacemaker. The colocation constraint basically guarantees that the virtual IP always stays on whichever node is currently elected as the master, because you never want your application IP routing traffic to a read-only secondary node, right? And the ordering constraint, just as critical. It guarantees that Pacemaker promotes the database to master before it even attempts to bind the virtual IP. If it binds that IP first, your apps are going to hit the node before the database is even ready to accept RAID operations, and that causes massive application errors. We definitely don't want that.
And now, Section 5, the climax, the live failover test.
Okay, let's actually see how this all builds into a live proof of concept. We've got our cluster, we've got our constraints, and our synced databases. We check our PCS status, and boom, everything is green. Node 1 is the master, nodes 2 and 3 are slaves, and our virtual IP is just happily routing traffic over to node 1. But what happens if we simulate a totally catastrophic crash? Say an administrator accidentally stops the SQL Server service on node 1, or maybe the server just completely loses power. How fast can our Linux cluster actually recover from that?
Well, when you watch the terminal during a crash, the speed is just incredible. Literally in milliseconds, the Corosync daemon detects a missing heartbeat from node 1. Within seconds, it immediately demotes that crashed node. Almost simultaneously, it promotes node 2 to master. And because we set up our colocation and ordering constraints so perfectly earlier, it seamlessly migrates the virtual IP over to node 2. The end result? Zero downtime for your connected applications. They literally just experience a momentary blip, reconnect to the exact same IP, and continue writing data as if absolutely nothing happened. It's awesome.
It's just a beautifully resilient architecture. Now, all the shell scripts, the T-SQL templates, and those specific PCS commands we covered in this explainer, they are all fully available on the GitHub repository linked in the source material. So considering all these exact configurations we've just decoded together, how will you adapt these automation scripts for your own air-gapped or highly secured environments? I want you to really dive into those scripts, map out your own deployment, and I'll catch you in the next explainer.